Yes. So, okay, last but not least, Stephan Wojtowytsch, who is currently at Texas A&M University, I think permanently, is going to talk about continuous time, stochastic gradient descent, and flat minimum selection.
Thank you so much, and thank you so much to Katie and Simone for inviting me to this wonderful workshop, and to everybody who has already given us such wonderful presentations. So yes, I'm going to continue a little bit in the vein of the previous talk and talk about the training of neural networks and stochastic gradient descent. So the outline of my talk is to talk a little bit about the loss landscape and the specifics of optimization problems in deep learning, and then to talk a little bit about the continuous time analysis and what kind of minima we see. So in class, the tasks in machine learning and classical numerical analysis are not that different in the sense that we've got a data set and we're trying to fit values yi at points xi, or at least that is the loss function that we minimize. And in the classical theory, we've got techniques and we know the bounds for that. We've got polynomial interpolation or spline interpolation. And we know that sometimes these methods work very well and sometimes these methods totally fail. So we've got the Range phenomenon as one example of that. And in modern interpolation, we've got a data set which is in a very high dimensional space. So we need new tools for that. We use neural networks if we want to. And one of the key features of neural networks is that they are over-parameterized. So in classical interpolation, we've got as many parameters as we've got data points, or if we don't trust our data points that much and assume that there's noise, we've got actually fewer parameters and we've got under-parameterized learning. And neural networks have challenged this classical paradigm of using under-parameterized function classes, and yet they seem to work very well, and it's still not entirely clear to us what the reasons for that are. So because the functions depend non-linearly on both the parameters and the data, it is not that easy to find optimal parameters. And what we do is to penalize a loss function that in the simplest case just takes the difference of the output that we would like to see and the difference of the output that we have, and then squares it, sums it up, takes the average. So we've got an optimization problem, and that is the problem that I'll focus on today. And that is, unlike the previous talk, for empirical risk, for empirical loss with finite amounts of data, and not for infinite data. So one thing to note is that if we've got a data set with n points, and we've got a parameterized function model, so we've got m parameters, n data points in our D, and the function is reasonably smooth in the parameters. And we assume that for any y1 through yn, there exists some parameter such that our function fits the data, fits the values that we'd like to see exactly. Then the set of minimizers of our loss functional is the set of parameters where our function fits the data exactly, and that is an m minus n dimensional submanifold of the parameter space. And if our function model is Lipschitz continuous in theta, then we can fit, and it's expressive enough to fit data arbitrary outputs at an additional point, then this manifold is non-compact. So the proof is very simple. It's basically we've got m parameters, n constraints, and formally we apply the regular value theorem and Saur's theorem, and that tells us that almost every pre-image of y here under the function where we just look at the outputs of the model and all the data points is a regular enough manifold. And for compactness, we just see that if we can fit arbitrary labels at one additional point, then we can take 2 points in our manifold that must be far apart because the output at the last point can be chosen arbitrarily far apart. So we've got a very high dimensional set of minimizers, which is generally a manifold and usually a curved manifold. So the big question that I was getting curious about is that there are many minimizers. There's a continuum of minimizers of this loss function. And some of them memorize the data set. So if you give your students a finite number of examples and tell them those are going to be on the exam, then some will understand the pattern underneath the examples and some will memorize the data set. And neural networks can basically do either. And the question is, what do we see, or why do we often seem to see the case that we actually understand some meaningful structure in the set? And so which minimizers do we find when we train our neural networks? And training to me will be following the stochastic gradient descent of the loss function. And the conjecture is that we find minimizers where the energy landscape is flat in some sense, because if it's not flat, then you've got small scale oscillations or instabilities where moving slightly could throw off something. But that's going to become more precise in a little bit. And something that I'm not going to talk about at all today is the conjecture that flat minimizers generalize better. And I think this is the first occurrence of that flat minimum selection conjecture, and it's been studied since. And so let's talk a bit more about the loss landscape of neural networks. So as in the previous talk, a neural network, let's say a shallow neural network, is a function that is just a sum AI sigma of some linear function of x. And if the statement is if we've got more neurons than data points, then we can fit any values at a given set of data points. So, and if we are in one dimension, then that is pretty trivial, because if m is greater or equal to n, and say we use Rayleigh activation, then what we've got are a bunch of points here. And our Rayleigh is expressive enough to allow us to do something piecewise linear. And so we can just interpolate that with a piecewise linear function with n+1 segments or something. So we can see that in one dimension, this is trivial. And in the multidimensional case, we just project this into some direction such that the one-dimensional projection of all the data points is different. And then we're back in the one-dimensional case. So neural networks are one of those function classes that can fit random labels. And any two-layer neural network, if you just reparameterize it, can be either expressed exactly or approximated by deeper neural networks that have at most like 4 times as many parameters. So you still get the ability to fit random data. Of course, this is very heavily over-parameterized since you've got n data points and n times dimension parameters. But that is not actually crazy bound for realistic cases where we've got thousands, tens of thousands of data points and possibly millions of parameters. So any two-layer neural network, what a two-layer neural network can do, also certain deep neural networks can do. Yes.
It's known that n parameters.
Yeah. Yes. You can definitely reduce this, but this is the easiest proof that I was aware of, because it's just a sketch on the board. And so under the same assumptions that we made above, L is convex if and only if the function is linear in the parameters, not necessarily the data points, but the parameters. And the sketch that I would give you is that if we've got a manifold of minimizers and the function model is nonlinear, then the set where it fits the labels exactly will generally not be exactly linear. So this is the set of minimizers. And then if I connect 2 points in the set of minimizers, some point on this line connecting two minimizers has to have a negative Hessian. So we've got and we can push this a little bit further under a bit stronger assumptions. So if we are minimizing the loss and the function class is nonlinear enough in the parameters, then the loss function will not be convex in the neighborhood of any minimizer, which means that typical learning guarantees from stochastic optimization may not capture exactly what's going on in deep learning. So that is a little bit on the loss landscape. And the question is, does this come from the fact that we have over-parameterized our model and we only use finite amounts of data? I'm going to argue that that is not the case, because let's just look at the ReLU activation function. Then we've got, again, these two-layer neural networks. Obviously, OK, we can reparameterize the neural network by just changing the labels on the neurons. That's boring. That disappears, for example, if we pass to the empirical distribution of the parameters. We've got another possibility that in the outer layer, we just choose the same parameters for W1 and B1 and W2 and B2, and we choose the opposite sign for A1 and A2. That also gives us a degeneracy in the parameterization. We've got a scaling that is fairly specific to ReLU. We've got an identity, and this is, I think, where things get a bit more interesting. So we can express Z as ReLU of Z minus ReLU of minus Z. So Z plus 1, for example, can be expressed as ReLU of Z minus ReLU of minus Z, which gives us the Z plus ReLU of 1. Or we can have we can just express the linear function inside and then have it outside. And so we've got many different ways of representing the same function. And the possibly most interesting example is, so if we've got a function just on the real line, which says, say, has the first derivative in BV, so a little bit less than W21, then we can recover f of x as a certain integral of the ReLU function. This is because ReLU, basically like the absolute value function, is a Green's function for the Laplacian in one dimension, because take two derivatives and you get a Dirac delta. This also characterizes these functions in higher dimension, where Rob Novak just applied a Radon transform, and then you get very similar results here. But for example, this means that if we can represent the Euclidean norm squared along the as a function which takes the x1 squared plus x2 squared plus x3 squared, so which has neurons that are all along the coordinate axes, but we can also rotate our coordinate system. And so we can have neurons pointing in very different directions and represent the same function. So there's a lot of degeneracy, even in the infinite data and infinite parameter case. So the representation of a certain function is generally very non-unique. And so you would not get rid of this set of this complicated set of minimizers. All right. So training, I said, is for me stochastic gradient descent. So that is, well, gradient descent is just, I take a little time step in the direction of the negative gradient of the loss, which in this case has this specific form, which is just how well I fit my data averaged over the data set. Stochastic gradient descent, I replace that with a small subsample of my large data set. I'm generally going to picture also batch size 1, but that is not a key feature here. In general, stochastic gradient descent can be thought of as a law where theta t plus 1 is given as theta t minus some step size eta times an estimator of the gradient, which gives me an unbiased estimate of the gradient. And for the analysis, I usually require some moment bounds. So there is a long classical theory going back to the 50s. If I've got certain moment bounds, what convergence can I get? And that does not necessarily capture what's going on in deep learning. Because so if I look at this loss function, I can calculate the gradient. I've given that to you on the last slide. I can calculate the Hessian, and I can calculate the covariance matrix of the gradient estimators. So that is the difference between the average misfit on the data set and the true misfit. And the gradient estimator, the noise intensity in the gradient estimator scales with the value of the loss function here. The way to think about this is I am at a global minimum if and only if I fit all my data the right labels at my data points exactly. So if I fit all the data points exactly, then none of my gradient estimators will give me anything else than 0 because that point is happy. So that is, I think, a bit like the observation that a function is 0 in L2 if and only if it is 0 in L infinity. And so I do fit all my data points exactly. So I don't experience stochastic noise when I'm at the global minimum. Whereas if I'm far away from the global minimum, then trying to fit the constraints on different data points may pull me in very different directions per data point than the global average. So I experience a lot more noise in high noise regions. And because I have much fewer data points than I've got parameters, the gradient, the noise in the gradient estimator has a very low rank. And so here you see these, if I'm at the global minimum, these terms are all 0. So that guy disappears. What I've got is this product of the gradients, which is roughly the same thing that appears in the covariance matrix of the noise. So as an approximation, something like loss times Hessian of the loss has been proposed, but not very well studied. And there are a few studies that concern the low rank of the noise. I'm going to focus on the other part. I'm going to focus on the fact that the noise intensity scales with the intensity of the loss. So this is just another way of stating this bound. So the expected value between the true gradient and the gradient estimator is bounded by some constant times the value of the loss function. And you can exploit that. I'm going to gloss over this a little bit. But if I've got an objective function where the gradient is Lipschitz, that is the standard assumption for simple analysis of gradient descent. And we've got an energy dissipation inequality. So basically, globally, our loss landscape looks like a valley, not a convex valley, but a valley nonetheless, where the set of minimizers may be a little bit curved. So this is a probably better assumption near the minimum of the loss surface in deep learning. And then I've got a family of gradient estimators that have the right noise intensity scaling. If my step size is small enough in terms of the problem givens, then I can prove that the expected value of my objective function decays exponentially fast along the stochastic gradient descent. And because the objective value decays exponentially fast, that actually implies that I converge to a global minimum. And the only thing that I want to really point out about this result is that we can keep the step size positive. That is a massive difference to the case of classical stochastic noise, where the noise intensity does not diminish at the minimum. And so that would give you an invariant distribution that is concentrated around the minimum, but not actually convergence to a minimizer. Whereas in deep learning, we usually keep our positive step size fixed and we pretend that it's small enough and that we would let it go to 0, but that's not what we do. And to an extent, I would claim we don't have to because our noise has a better structure than, say, in classical mechanics. And we can also push this further. So if our landscape doesn't look like a valley globally, but only on the set where the loss is high and the set where the loss is small, and the noise has some nice structure, then we can also prove exponentially fast convergence almost surely, but with possibly prohibitively large constants. So the idea here is that where the loss is high, either the gradient or the noise helps you, and where the loss is already low, the noise is not strong enough to mess things up for you. Yeah, here you see a little bit the setting that I was describing originally. If you've got noise that doesn't vanish at the minimum, you get this kind of invariant distributions for stochastic gradient descent or Langevin dynamics in this case. If you let your learning rate decay like we do in classical analyses, then you still get something that is bimodal for reasonably large times. Whereas if your noise actually goes to 0 at the global minimum, then here still we have a point cloud around a local minimum. But once it penetrates this energy barrier, once it gets into the potential well of the global minimum, then it converges to the global minimum very quickly. And so this is a kind of a capture situation where once you get into the region where you converge to the global minimum, you actually never escape them. All right, so that is on the convergence and on the loss, but I promised you a little bit more in-depth analysis of what kind of minima we converge to. And the discrete time analysis for the time stepping scheme is actually really hard. So let's look at what a continuum model would tell us. And here, instead of having the discrete time stepping scheme, I'm going to pass to a stochastic differential equation, which has the same kind of covariance structure as the discrete scheme, but that allows me to neglect the effects from finite positive step size. And so if we solve the continuous time stochastic gradient descent SDE, then the law of the parameters solves this PDE. And so to actually be able to do something analytically, I assumed a particularly simple covariance structure, which is still isotropic, but no longer homogeneous. Namely, the noise intensity has the correct scaling, but it does not capture the low rank features that I was telling you about earlier at all. So I'm just having some constant times the value of the objective function that I'm trying to minimize times the identity matrix. And then I can reformulate my PDE for the invariant for the evolution of the law of stochastic gradient descent. And so if here we see that this is the PDE, a stationary solution, well, if this is constant, then the gradient is constant, and then the divergence is, then the gradient is 0, and so is the divergence. So there exists a trivial solution to this invariant distribution problem, which has precisely this structure. And the 1 over eta sigma is essentially given by how strong my noise is. So if the noise is low, then this concentrates a lot more in the regions where F is low. And so we can apply a Liouville theorem from the 70s to show that if f essentially grows polynomially. So if the logarithmic gradient is bounded by a constant divided by 1 over modulus, then this is in fact the only non-negative solution to this stationary PDE. And in particular, there may not be any invariant distributions. The noise intensity gets very high at infinity, and that may actually carry you away and prevent SGD from converging. So for comparison here, if we've got some constant times f to the -1 over eta sigma, and in the classical noise case, we've got this exponential. This becomes particularly interesting if f is allowed to be 0, because then here we still have something bounded, whereas here we see that we've got something that may remain integrable, but which concentrates a lot more sharply at the set of global minimizers. So we see something similar to what we observed before. And obviously, I'm making the assumption here that the infimum is positive, and then I'm analyzing the distribution if f is allowed to be 0. So there are a lot of gaps in this, but this was very curiosity driven, and I think there's a lot more to do in this. So if I assume that I've got a density which an objective function which vanishes on a high dimensional manifold, and that the Hessian has full rank, so that the function detaches from 0 quadratically, essentially, then I can get an invariant distribution which is integrable, and we can analyze the invariant distribution just at the critical threshold. So for small positive noise, the invariant distribution collapses to the manifold of minimizers, and that's all we can say. For noise which is a little bit stronger, we've got an invariant distribution that is somehow focused around the manifold of minimizers. I was curious about precisely what happens if we approach this critical threshold. There's a question, yes.
Something clear, I don't understand. If I take a distribution that is supported on the zeros of x, that is also invariant. Yes.
The invariant distribution is not unique. So, and I can tell you something. I will tell you something about which invariant distribution you converge to in a very special setting.
So, but in general, you don't know whether.
No, so I don't know whether the analysis that I'm doing here is meaningful. I think there are situations where we can prove something more than what I'm going to tell you today, but I do think there are a lot of gaps. I do think this is a bit understudied. And so here I was looking at the invariant distributions with noise that scales like in machine learning, and with classical noise for the same objective function. And so if I approach the critical noise threshold where everything collapses to the manifold of minimizers, either here as eta sigma approaches the critical noise threshold, which is positive, or as the temperature goes to 0 in the classical setting, then here I get something that is proportional to the determinant of the Hessian in the directions orthogonal to the manifold of minimizers. Whereas here I get a different kind of average depending on the Hessian orthogonal to the manifold of minimizers. And these two functions have the same homogeneity, but they are not the same. So if I just look at the simple setting of a codimension 2, then a Hessian orthogonal to the manifold of minimizers is, say, 1, lambda. Then the classical noise, where I take the determinant and then take the negative square root, would give me lambda to the -1/2. So essentially, if I've got an eigenvalue that is small, that tells me that the objective function is flat, and that is a minimizer that has high density. So in that sense, even for classical noise, you would expect to converge to somewhat flat minimizers. Whereas if I take noise more like the one that we see in machine learning, then I don't get the geometric mean of the eigenvalues. I get the algebraic geometric mean, which interpolates between the geometric mean and the algebraic mean. And so this goes to 0 like 1 over logarithm. So here, if I want to say that a minimizer is flat for machine learning scaling noise, then I would have either to have both of my eigenvalues small or one extremely small, whereas here in the case of classical noise, one small eigenvalue is enough. So I get some different notion of flatness, and that was one of the main interests, to see how can we actually derive a good notion of what it means for a loss function to be flat, because I think that's not been done. And so I'll gloss over this, but I promised you I'll tell you. So if my if my objective function looks something like 1 plus theta squared, especially on large scales, then I've got a unique solution of this evolution equation, and I get convergence to the invariant distribution. But this is if my objective function is positive. So that's probably no surprise that I get precisely this type of convergence. And the proof essentially uses a Poincaré-Hardy inequality due to Bonforte, Dolbeau, Grillo, and Vasquez, which was used to analyze fast diffusion. But this is kind of a linearized version of that. Now, we can push this a little bit further, but under strong assumptions. Namely, I can't actually give you something that vanishes on a manifold yet. I can give you something that vanishes at a finite number of points. And even then, I need to make a very strong scaling assumption between the noise intensity and the dimension that I'm in, because otherwise I run the risk of either running away to infinity or collapsing onto my finitely many points. So this is the only situation where I can say something about an invariant distribution which is a density with respect to Lebesgue measure. And then I need that essentially the objective function detaches from 0 a little bit faster than quadratically at the minimizers and grows a little bit faster than quadratically at infinity. And if I've got this specific kind of a behavior, then I can prove Poincaré-Hardy inequality also in this setting. And then I can again prove convergence to an invariant distribution of the type that I've analyzed. But like I said, there are many open problems here. There is the validity of the continuum model for the SDE in the long-term limit, and analyzing the invariant distribution for that. There is the fact that I've proposed stochastic noise, which has full rank. There is the fact that I'm making some growth assumptions that are not necessarily valid. There is the fact that I'm analyzing an SGD version, which is not the random pass through a data set, but which is basically every data point has independent noise, every time step has independent noise. So there are a lot of open problems here. But I think this is a really exciting and important problem, because in training neural networks, the good behavior does not come from the loss function. So it needs to come from somewhere else. And so understanding what this training algorithm does is actually key to understanding why neural networks work so well. And with that, I would like to thank you. And yeah.
Thank you for an inspiring talk. Question? Yeah, Yakush.
Thanks. It's a really nice talk. I'm just a bit confused with you have an assumption on the estimator of the G, the stochastic. So you have this assumption between expectation, like here over here.
Yeah.
The second assumption is bounded above by f theta. Is this assumption or is this a consequence? Or?
So this is an assumption that I'm making for this theorem. This is a realistic assumption for deep learning models in the sense that the noise intensity goes to 0 as you approach the global minimum, which is 0. And in the sense that the noise intensity goes up as you go further away and have bigger misfit in your points. I think a more realistic assumption would be something like expectation of gradient minus grad f squared is smaller or equals c to the 1 plus norm theta squared f of theta, or something like that. That I think would be a reasonable assumption, probably possibly a slightly different growth. But this is the setting that was straightforward to analyze, so that's where I started.
But if I compare this condition with just the PR condition above, it feels like it's just opposite of each other. This PR condition, its f is less than equal to the gradient of the norm. Now it seems to
as a consequence of these two conditions together, you also get a bound that the is smaller or equal to sigma times expectation of gradient. I guess we are doing this pointwise, so this is also smaller than gradient f squared. So you're right. That this basically these two conditions together also tell me that the oscillation in my gradient estimator is on the same size as the gradient itself. If sigma is small, then that would, for example, tell me that I'm probably in the right half space, but sigma can be much larger than 1. It just comes at a cost that you need to take a smaller step size.
Okay.
So yeah, but those two conditions definitely interact here.
Thanks.
Yeah, I was wondering about these two different measures on the manifold, like one with the scaling, and the one of the different scaling. So you mentioned the example of the two codimensions, right?
Yes.
So, but I was interested in the more codimensions and dependency on the dimensions, really, because one seems like a trace and the other seems like a little.
So yes, here if you've got codimension here, this one is very easy to understand in any dimension. The first one is a bit harder because you need to solve an elliptic integral, and that basically gives you this algebraic geometric mean, which is essentially a compromise between a plus b half and square root a times b. And I can definitely tell you what happens with the first one. I've not actually looked at what happens with the second one in higher codimension, and I really should. But the first one, if you've got just ones and then a lambda, then it wouldn't be lambda to the -1/2. It would be lambda to the -1 over codimension. But yes, that is a calculation that I should do.
Yeah. Quick clarification question, perhaps. So this result was essentially shown, or something similar along these lines was shown in a paper by Belkin and Basili and Ma. Right? So they exactly make this assumption and show under for exponential convergence for SGD. So, and also there's another result. under the same assumption, SGD escapes saddle points and conveys to local minimizer at a deterministic rate.
Yes.
So, what's the difference between those existing results and this analysis or this finite time?
In the finite time step regime. So the only results that I was aware of in the same noise scaling are for convex energies instead of the PL condition. But if you send me the paper and it's been done before, then I think I definitely want to have that reference. The other thing is that I think the more interesting part is the kind of global convergence result, which makes assumptions on the loss landscape essentially where the loss is very low or where the loss is very high, but you make very little assumptions on what the loss landscape does in between. And so it captures a larger class of functions. And so this I've not seen done anywhere before in this form, especially because there you really need to go a lot into the analysis of the fact that once you're close to a global minimum, you don't really go away from there anymore. So I think that is the main technical. So this theorem that I kind of glossed over is probably the main technical contribution of the article.
Okay, one last question.
This theorem, I just understand you don't assume basically, you assume very little of this function, right? So you cannot expect to get the dimension. Right?
Oh, no, I don't.
Potentially, this is exponentially.
Yes. This is exponentially in the dimension, and I don't think there's any way around that. There are computational hardness results that tell you if I don't make assumptions, then I can't do better. So in a sense, this is a glorified grid search, but I think the fact that you can prove a global convergence result for SGD at all is already kind of interesting. And then maybe if we can understand the geometry of the loss landscape better and make finer assumptions, then we should be able to get better rates. And I think that is also one of the things where escape from stationary points and analyzing saddle points and bad local minima, where possibly the low rank of the noise actually helps you. Because if you've got very high rank noise, then you're oscillating in a lot of random directions. Whereas if you've got low rank noise, which focuses kind of on the main important directions, then you've got a much better chance to escape your bad local minimum, because the oscillations kind of are only in the relevant direction. So the rank of the noise, it wouldn't be the full dimension that matters, but the rank of the noise. So I think there is some room for improvement there.
All right. So this resulted in a lot of discussion. Thanks, Stephan.